In this video, we will be covering the node voltage and mesh current methods, but this will be the second part. This is an extension of the previous one, but we will have some more complex examples that will introduce some issues you can encounter when using these methods. Now in this circuit here, we see that we have two independent voltage sources. And when we set up our circuit a certain way, you'll see that we'll kind of have this new issue we'll have to work around. But as proceeding as normal, we have to assign our reference node. We'll start with the node voltage method. So for this example, I'm going to assign the reference node as the central node here, and we'll set that as 0 volts. Continuing as normal, we can assign all the other nodes, taking care to identify all of them. So this top node here, this is all a node, and then we can label that V1. The next node here, we can label as V2. Of course, we have our central reference node. We can leave that as is. And this is also a node that we can label V3. Now these next two nodes, some might miss, but these are in fact nodes as well. So we'll label these V4 and V5. And then this whole bottom portion is its own node, and we can label that V6. Okay, great. Now the objective is to obtain some kind of system equations relating all these different nodes using KCL. Now, again, I use the convention of all the currents exiting kind of a junction. So we can start with our top one. We see assuming, using my convention where all the currents are kind of leaving, we can perform KCL, and remember that this means that the sum of all the currents exiting this junction must equal 0. So we'll start with this current here going through this 10 ohm resistor. So using Ohm's law, V over R, we can find the voltage across that resistor, which will be V1 minus V2 divided by the resistance, which is 10 ohms. So that's the first current. We can cover this current now. For the 50 ohm resistor, that'll be V1 minus our reference, which is 0 volts. You can leave it as is or include the 0 to be explicit, divided by the resistance, which is 50 ohms. Now the third will be this current here, and that'll be V1 minus V3 divided by the resistance, which is 4 ohms. And again, KCL states that the sum of all those currents will equal 0. So this will be our first KCL equation. No issues there. It's a different color. We can start with this. The next one will be V2 we can do. And remember, this is KCL at node V1. So V2, again, assuming all the currents exiting. Now this is an arbitrary convention, but I like to use it to stay consistent for me. But we can assume we can go through the 10 ohm resistor this way. The current there will be V2 minus V1 over 10 ohms plus this current here, which will be V2 minus the reference of 0 volts divided by the resistance, which is 20 ohms. So rewrite that. And then the final current will be the one through the 4 ohm resistor, and that'll be V2 minus V4 over 4. And KCL states that's equal to 0. This is KCL at V2. Great. So proceeding as normal, we can do the central node now, where we have 4 distinct currents. So we can do the 50 ohm one first. Let's do a different color. So the 50 ohm resistor will be 0 minus V1 over 50 ohms. Then the next one will be this 8 ohm, which will be 0 minus V3. Remember, that's the current exiting that node, so it'll be over 8 ohms. Let's just rewrite that. The next current we can do is a 16 ohm resistor, which will be 0 minus V6 over 16 ohms. Then finally we can do current going through this 20 ohm resistor, which will be 0 minus V2 over 20, and the sum of all those currents is 0. It's KCL at our reference. Great, so we've obtained those. Oh, there's one more actually. We can do KCL V3 here. So current through here will be V3 minus 0 volts over 8 ohms. Then through the 4 ohm, V3 minus V1 over 4. And then finally through the 8 ohm resistor here, that is V3 minus V5 over 8 ohms. And that equals 0. Okay, those are all the nodes we can kind of find using our traditional method. Now we can continue with this bottom node, but we will see that this is kind of where the issue arises. You'll notice that deriving a current for these two branches will seem odd, as we have kind of a voltage source impeding us on both sides. We have the 60 and the 90 volt. And the way that our ground is assigned, these voltage sources are connected to two non-reference nodes. So these are both non-ground. So these nodes here for this branch are non-ground. They're unknown to us, and same thing here. So that kind of leaves us unable to perform KCL normally. So what we have to do here, these things are, these branches with these voltage sources, these are called supernodes. And supernodes occur when you have a voltage source, an independent voltage source that's connected to two non-reference nodes. So we can't form a KCL equation using our normal methods, but fortunately, with a bit of critical thinking, we can see that these nodes, we can actually create a relation between these two nodes, and which will allow us to get two equations. And here we can see that if we want to relate for this branch these two nodes, we can see that we can actually convey the information we need. V4, you can see travel here, there's a 60 volt differential there. So V4 plus 60 gives us the potential at V6. And then same thing over here actually. We see that V5, this time it's minus 90 because of the positive terminal there, will give us the voltage at V6. Now what we have here are what we call supernode constraints. That is the technical term for them. And since we've obtained these new equations, these are in fact two equations that are perfectly valid that we can use in addition to these other four above that will allow us to progress as normal. But this is the primary point here, is that when you have kind of what we call a supernode here, kind of label this here to be explicit. These are both supernodes kind of. We have to use that to form these two new equations. If we recall that these are independent voltage sources, so the current through them is dependent on kind of the rest of the circuit. It will provide the potential difference regardless of the current going through them. So that's kind of where we have to be careful with our normal KCL. But once we have our equations, we can solve this using our normal methods with simplification. Now, once you obtain your equations, what you're going to need to do, like the previous examples we've done, is simplify them to kind of their most reduced form. So here, again, you want to kind of find the common multiples for each equation, and that'll allow you to get more simple equations like this, which you can then simplify further into the final equations that you're going to use. Okay, now that we've obtained our equations, brought back the circuit for a visual. But as I mentioned, when you're solving a large circuit like this, you can solve it by hand, but it will be extremely tedious, and I definitely recommend translating this into matrix form and then plugging it into a graphing calculator or whichever utility you have. Here I'll kind of show you the process of doing that. So I've kind of we've gotten our equations that we've obtained in the previous steps, and again, since we have the nodes labeled 1 through 6, so we're going to have a 6 row by 7 column matrix. So we can kind of start with the first equation. So V1's 37, so that'll be up here like so. Then we have V2 was negative 10, V3 was negative 25. We have 6 other nodes, so the 4, 5, and 6 will be labeled as 0, and then it's equal to 0. So that's the first equation, and the second one we'll do follows suit. That's negative 2, and then 8, followed by, there's no third variable, so it's going to be 0, and then negative 5. Remember, when you kind of have to skip a node, that's going to be an empty entry in your matrix, and then 5 and 6 are 0. Okay, I've done some more simplification. Also remember to check your matrix entries. I misentered those, and you will in fact get the wrong answer, so make sure to check that. But when you plug it into your calculator, whatever utility you have, into using reduced row echelon form, you should get a matrix that looks like this. And these are our node voltages. All these here, this is the first entry, this is V1, this is V2, this is V3, V4, and so on. Definitely the faster way to solve this is just to input into a matrix. But these in fact are your solutions. And you can kind of do a sanity check to make sure you are actually getting an answer that makes sense. So you can check that. So we know that V6 needs to be 60 volts higher than V4. So we see negative 9.762 for V6 is in fact 60 volts higher than that. And the same thing for here. We can see that V5 should be 90 volts higher than V6. And we also see that's consistent. For the second circuit, we're going to approach this using mesh current analysis. And traditionally, in mesh analysis, you would look at your circuit and identify each mesh that is present, which are the smallest enclosed loops, and assign them each a current variable that we will subsequently use to write KVL equations for and solve. So we can do that. So we can start with the bigger loop here and assign that a current variable I1, say. For the top right loop, we could say this is I2, and we could say this is I3. Again, this is arbitrary. It does not matter which variables you use, as long as you stay consistent. So once we've done that, we can begin to write our KVL equations. And remember that KVL states that the sum of the voltage drops of a closed loop is equal to 0. So remembering that, we can start with our I2 loop. Now the I2 current, we've assigned it in the clockwise direction, so we can assign polarities like this to our resistors, as so, since we are going in the clockwise direction, and we can write a KVL for it. So KVL at I2, so starting with a 2 ohm resistor, the current going through it will be I2, so the voltage drop according to Ohm's law will be minus 2 ohms times I2. For the 3 ohm resistor, we need to take care to notice that this is the intersection of two meshes, I2 and I3. And because of that, the current will be I2 minus I3. So the voltage drop across this resistor will be the minus 3 ohms times the current, which is I2 minus I3, because we are, again, on the intersection of these two. Likewise, for this 1 ohm resistor here, the current going through it will be I2 minus I1. So you see that. So this is our first equation. This will be equal to 0. Now, what we notice when we begin to do the KVLs for the other loops is that we do not know the voltage across this independent current source. It's unknown. All we know is that the current through this branch will always be 7 amps, regardless of the voltage across it. So in this case, what we're going to have to do is we are going to merge the I1 and I3 meshes together so that we can remove kind of this current source from our analysis and write a KVL loop for it. So the KVL loop is going to actually look like this. It's going to go around here like this. It's going to kind of enclose that independent current source, because again, we do not know the voltage across it. We can't write a KVL for it. So we can write our KVL as normal now, starting with the 7 volt independent voltage source. So that'll be 7 volts, because the current's going this way, so we're going to gain 7 volts. 7. Now the 1 ohm resistor, since the current now is going this way, that'll be I1 minus I2, so that'll be minus 1 times I1 minus I2. Again, the current, the direction of the current we're going in will be the first variable there. Now, since we're going this way, we're going to be with the 3 ohm resistor. So the voltage across there will be minus 3 times I3 minus I2. Remember that we are, once again, intersecting 2 meshes. For this 1 ohm resistor, it'll just be minus 1 times I3, since we're not intersecting any mesh there. And that'll be our full KVL equation there for kind of our I1, I3 super mesh. And that's what we're doing here. That this method is called kind of super mesh analysis. Kind of the analog of supernode from the previous example. Now you'll notice though that we have only 2 equations for 3 variables, so we can't solve this, but we're going to use this independent current source to write what we call a super mesh constraint. So we know that the current through this branch that is intersecting the I1 and I3 mesh will always be 7 amps. That is definitionally what independent current source will do. So we can state that the I1 minus I3 current, since I1 is in the direction of the current source, is always 7 amps, and that's where we kind of derive our third equation to make the system solvable. So this is our super mesh constraint. Okay, so once you've gotten your equations, you can simplify them as I've done, get them to their most reduced form, and you can solve this system, well, again, whichever way you like. You can put it into a matrix, do substitution, or whatever you'd like. But what you should end up with is that your I1 mesh will be 9 amps, your I2 mesh should be 2.5 amps, and your I3 mesh should be 2 amps. Now, to exemplify how this has solved the circuit, we can now solve the voltage for any node, since we now know the current going through the meshes that we've assigned. So say, for example, that we want to find the voltage at this central node here. It's unknown, but with the mesh currents we can achieve this. So first we want to assign an arbitrary ground, just for reference. Again, this is arbitrary, so we're just going to say it's at this bottom node here. That way we can say that this top node is 7 volts, because of course of this this independent voltage source. So this top node is 7 volts. This central node is unknown, but we know the current going through this 1 ohm resistor. Since it's I1 minus I2, and this here we can erase this real quick. We know that I1 minus I2 will give us the current through the 1 ohm resistor. The I1 mesh, as we found, has a current of 9 amps, and the I2 mesh has a current of 2.5 amps. So I1 minus I2 will be 9 amps minus 2.5 amps. That's 6.5 amps. Okay, so we know the current going through the 1 ohm resistor, and with Ohm's law we can find the voltage across it. So the voltage across the 1 ohm resistor will be 1 ohm times 6.5 amps. Since it's a voltage drop, it'll be minus. So we know that the voltage across the 1 ohm resistor is minus 6.5 volts. So we know the voltage of the top node, which is 7 volts, and we know the voltage across the 1 ohm resistor, which will be 6.5 volts. So we now know that the central node has a voltage of 0.5 volts. So using this kind of method here, you can find the voltage of any node, and we know the current through all the components. So you've solved the circuit.